Welcome back to solving advection equation using central difference or finite differencing. So last time we talked about how we can use forward Euler or backward Euler to solve advection equation. Today we're going to talk about how we can basically use central difference and improve the accuracy of our numerical discretization to solve advection equation. So the equation we're talking about is du dt plus v du dx equals 0. Where v is the velocity of, you can think of a flow, and u is the concentration of species in the fluid. So today we're going to talk about how we use central difference to discretize du dx, as you can see in this equation, where we are using I as the index for x. This piece is the central difference for the discretization of du dx. And if you also discretize the time derivative of u with respect to time, then we're going to have on the left side, so we're using forward Euler in time, we're going to get un plus 1 minus un both at xi, because we're taking derivative with respect to time, so we do not change the I index. And then on the right side, we're using central difference in x. So we're going to have minus v because we move this term to the right side. So they get minus v, and then we have ui plus 1 minus ui minus 1, both at time tn, because we are doing forward in time. So forward in time, the right side should be at time t equal to n. And then divide by 2 del x, because this is central difference in x. Alright, so the unknown here would be ui n plus 1, and we move everything at time n to the right side. So we're going to get equals ui n minus v dt dx times ui plus 1 at time n minus ui minus 1 at time n. Alright, so now we're going to claim that this method that we derived here in equation 1 is unconditionally unstable. So we had this experience before that whenever we go to explicit methods like forward Euler, we ended up having an unstable method. And this is actually another case of getting unstable method using forward Euler. And so we're using actually forward Euler in time. So that's why we get unstable discretization or unstable finite difference scheme. So let's get into the details of why this is unstable. So we're going to do von Neumann stability analysis, and if you remember, to do that, we replace our generic variable u and j, where n is the time index and j is the x index. We're going to replace this by some parameter c, which is the magnitude of the perturbation, raised to the n, which is the index of the time, and then times exponential of I, imaginary number, times k, some integer number, and then times x sub j, where the j is coming from the j in the x index. Alright, so I'm going to replace our y and j or x and j by this composite term. And if you do that, if you replace every term here in equation 1 by this new formula, on the left side of equation 1 here, we get c raised to n plus 1 exponential of I k x j, because this is at time, well, you can think of this as uj n plus 1 instead of ui. So we're going to replace all the I index of j. This doesn't actually change anything, we're just renaming the index. Alright, so this is going to be c raised to n plus 1 power, and then exponential of I k times xj. And the reason we actually replace all the i's with j's is because we're going to have another I for the square root of minus 1. That's why we need to replace all the i's with j's to avoid any confusion. Alright, on the right side we have c raised to n exponential of I k xj, and then minus v dt dx. Now we're going to have 2 dx. I think there's a typo here, it should be 2 dx. And then times, from here we have exponential of ikxj plus 1, and this one is exponential of ikj minus 1. And then the xc factor is going to be xc raised to n power here, and then xc raised to n power here as well. So that's why we get these two terms. All right, now what we do is we do a lot of cancellation, so we can cancel xc raised to n power from both sides. We have xc raised to n power here, 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 here. We also cancel out exponential of ikxj. We have one here, one here. This one, xj plus 1, can be written as xj plus del x, and xj minus 1 can be written as xj minus del x. So then we can cancel out ikxj from both sides. And after we do this, what we get is the following. So from here, we are left with xc equals, from here, we're going to left with 1 only because everything's canceled out. And then minus v dt over 2 del x times, from this term we get exponential of ik del x, because we cancel out xj from both sides, so this actually ends up being xj plus 1 minus xj, which is del x, and this ends up being xj minus 1 xj minus 1 minus del x, or minus xj, which is minus del x actually. So that's why we get exponential minus ik del x here. Anyways, so now we can simplify this using Euler's formula for trigonometric functions. We get c equals 1 minus, we're going to replace this by alpha, just a change of variable as before. So now I'm going to have alpha equal v dt over 2 del x, and then times this thing is going to be, you can write this as cos of k del x plus I sine k del x, and this guy is cos k del x minus I sine k del x. Then the signs cancel out, because of the minus sign, because of the minus sign, cos cancel out. So we get 2 times 1 I sine k del x from here, another I sine k del x from here, so totally we get 2 I sine k del x. This is c. Our goal is to show that c is bigger than 1, because if something is bigger than 1 raised to n power over time, this actually will grow up, and then it's going to spoil our numerical solution, which means the solution blows up from a perturbation. So let's see how we can prove that c is bigger than 1. Well, magnitude of c is bigger than 1. So what we do is, because this is an imaginary number, we're going to multiply this by its complex conjugate. So this is c, this is c complex conjugate. So we use this theorem from algebra that this multiplied by that is equal to the term which is fixed in both parentheses, and then minus the term which is changing sign raised to the second power. So it's going to be 1 minus this thing squared, and then so then we get 2 squared is 4 alpha squared sine k del x squared, and then I squared is going to be -1, which cancel out that -1, so totally get positive. So we get 1 plus 4 alpha squared k sine squared of k del x. Alright, so we know that all of these are positive, so this term is always positive. 1 plus any positive number is bigger than 1. So we proved that c is always bigger than 1, which means central difference in space and forward Euler in time is unconditionally unstable, because the magnitude of the perturbation is always bigger than 1. So hope this shows, or it's convincing enough to say that forward Euler in time and central difference space is unconditionally unstable. This also tells us another thing, and that is, doesn't mean that every time you increase the order of accuracy, like this one is second order in space, because we're using, if you remember, we're using central difference in x, right? Central difference in x is a second order approximation, which means it's more accurate than first order, but still doesn't solve the problem. The problem is we're still getting unstable method. So increasing the accuracy doesn't mean that you get a well-behaved numerical technique. All right. So now what we're going to do is now we're going to crank up the accuracy of the t as well. So far we did central difference in x and forward in time. Now we're going to do central in time, central in a space. So this method is called Leapfrog. So we're going to get back to this and see why it's called Leapfrog, but for now let's look at the accuracy and stability of central in space, central in time. All right, so this is the central in time now. We fix the j, we go n plus 1, n minus 1, we subtract them, divide by 2 del t, so this is central in time. And on the right side we have central in space as before. We keep the highest time index, which is n plus 1 on the left, and move everything to the right. So you get nj, n minus 1j from here, move to the right side, so you get a plus sign. We also multiply through by 2 del t, so we get minus v 2 del t, and then divide by 2 del x, so as the 2 cancel out, we get v del t over del x, and then this piece is just left over, so we get u nj plus 1, u nj minus 1. Alright, so just to remind you, this is the second order in time and second order space, because we're using central difference in time and space. So we're going to do a stability analysis. We replace all the terms ujn by x raised to n power exponential ik xj as before. So this is coming from the first term. This term is coming from the second term on the first term on the right, and then minus, we're going to call this alpha, and then times from here we get x raised to ik xj plus 1, and then from this term we get xcn exponential of ik xj minus 1. Again, we cancel x raised to n power from both sides and exponential of ik xj from both sides, and at the end of the day we get xc from the left term, and then 1 over xc from the first right term, and minus alpha. C cancel out, so you get exponential of ik del x minus exponential of ik minus del x as before. Replace this by trigonometric function, we get this. We multiply through by xc, move everything to the left, we get that equation. It's a second order in xc. The goal is to prove that xc is bigger or less than 1. So we're going to solve this equation. And this is a quadratic equation. We get basically find the root of this. So then xc is plus minus square root of this thing minus I times alpha sine k del x, and the I is coming from actually the linear term. All right, so we're gonna look at the magnitude of c. That means we have to multiply this guy by its complex conjugate, which is shown by c star here. All right, so after we do this, we get the magnitude of c squared is equal to this, which because when you multiply this by its complex conjugate, you get the first term squared. Well, this term squared minus this term squared. And if you do that, knowing that square root of I minus 1 raised to the second power is negative 1. So, right, so now, yeah, so this is the c raised to the second power. Now, if you look carefully here, if alpha is less than 1, so let's assume alpha is less than 1. If alpha is less than 1, this term is definitely less than 1. And then 1 minus that is also less than 1, then the square root of this thing is always positive. All right, so we have a real number here and an imaginary number here. So after we get the c squared, we look at this. You see that we can cancel alpha squared sine squared and alpha squared sine squared. So totally get 1, which means the magnitude of c doesn't change. It's always equal to 1, so this is stable. That means if alpha is less than 1, the central difference in time, central difference in space is always stable. So in the next video, we're going to see if what happens if alpha is bigger than 1. So stay tuned and thanks for watching.